Hello, everyone. I hope you're all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Our speaker today is Suzanne Staggs, who is a professor at Princeton University. My name is Thomas Puzia, and together with Evelyn Johnston, we have organized today's webinar for you. As in previous webinars, we have arranged for simultaneous language interpretation by Mr. Patricio González, who will be simultaneously translating for us into Spanish. En sus dispositivos, pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana del Zoom y seleccionar español. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA, for its Spanish acronym, for making this series possible.
Thank you so much for all your feedback and comments. If you're watching this via a recording on YouTube, please leave your comments below. If you would like to support the Golden Webinar series or give us feedback, please send us an email. And if you have any questions during the talk, you can type them into the Q&A window, and you can also upvote questions that other people have asked and comment on them, and we'll select the best questions for the discussion after the talk. Before we begin, I would like to briefly introduce our other panel members who are with us today. As usual, we have the speaker, we have Suzanne, we have Patricio, who is our interpreter. From the faculty at the Institute of Astrophysics at PUC, we have Rolando Duner. We also have several students. We have Manuel Solimano and Enrique Paillas. And we have the great pleasure to welcome our guest panelists today. We have Julie Nantais, who is a professor at the Universidad Andrés Bello here in Santiago. We have Cristobal Sifon, who is a professor at the Pontificia Universidad Católica de Valparaíso, and Julio Navarro, who is a professor of astrophysics at the University of Victoria in British Columbia in Canada. And finally, we have our excellent team of Q&A managers, Daniela Fernandez and Carol Rojas.
It is our pleasure to introduce Suzanne Staggs as our speaker today. Suzanne studied for her undergraduate degree in physics at Rice University, finishing in 1987, before moving to Princeton University for her PhD, which was awarded in 1993. Following her PhD, she was a postdoctoral researcher at the University of Chicago for 3 years before joining the faculty at Princeton University in 1996. Her work focuses on experiments to make measurements of the cosmic microwave background radiation, which was created during the epoch of recombination in the early universe, and thus is some of the oldest electromagnetic radiation in the universe.
Suzanne is the PI of the Advanced ACTPol project, which is the current generation of the Atacama Cosmology Telescope, also known as the ACT. The ACT is a 6-meter telescope located in the north of Chile, which is creating maps of the fine-scale features in the cosmic microwave background. These maps will provide further explanation of how the universe has evolved to its present-day state, and will address questions about the properties of neutrinos and the nature of dark energy and gravity itself. And today, Suzanne is here to tell us about her work charting the trajectory of the universe with the Atacama Cosmology Telescope from the initial conditions through the structure formation to the era of dark energy domination. So over to you, Suzanne.
Thank you. Let me just share my screen. All right, thank you. So I'm really delighted to be here today, and thank you very much for inviting me. I only wish I could be there instead, but this is pretty good. So I'm starting the slides with this lovely gritty photograph of the Atacama Cosmology Telescope that was taken by Rolando Duner from one of his drones. And I wanted to start with such a gritty type photo because there are two things that I'd like to do today. The first is I want to show you something that we've done recently with the cosmic microwave background, or CMB maps, from the Atacama Cosmology Telescope, which we actually often call ACT. But I also want to show you some of the gritty details of how you go between photons and the cosmological results that we are touting now. So the outline of the talk is here. I want to start out by defining the cosmic microwave background as something which sets initial conditions for a problem for the universe, and then talk a little bit about the ACT instrument, and then get to the recent result we've had with ACT and the parameter H naught, which is a parameter that describes the present expansion of the universe. All right, so I subtitled the talk Predicting the Universe Today from Looking at the Past with a Big Dish in the Desert. So this is the CMB as initial conditions is the part about looking at the past. So before launching into that, let me just talk about some of the empirical features of our universe. So we look around and we see that the universe is expanding, and we know that by the fact that essentially all other galaxies are receding from us with speeds that increase with their distance from us. And that was pointed out by Hubble some 90 years ago. And the slope of the line in the, over here, the slope of the line is that Hubble's parameter H naught. And then another truth about the universe is that it appears isotropic roughly on the largest scales. So you can see that in the lower picture over here, which is showing the distribution of galaxies which are observed in the infrared. And you can see that the number of dots is approximately isotropically distributed. But on the other hand, the background of the slide is this gorgeous picture from the ultra deep field from Hubble Space Telescope. And you know, one thing that you can't deny about this picture is that it's showing this enormous dynamic range where you have galaxies that have black holes in their center, and then in between you have the emptiness of space. So the universe today is highly lumpy. So a resulting hypothesis from observing those facts, those empirical observations, is that the universe is evolving. So it's evolving from an even more homogeneous state than the one we see when we look at the large scale distribution of galaxies. And the reason that we know that is because structures are forming all the time from the sort of inexorable action of gravity from any small inhomogeneities. The CMB maps that earlier uniform state. So this picture in the inset is from the CMB measurements that were made at the end of the last century. The two circles are just showing the northern and southern hemispheres of the celestial sphere. And just if you look at the color bar, the color bar goes from minus 100 millionths of a degree Kelvin to plus 100 millionths of a degree Kelvin. So those are very, very small fluctuations. And then the background of the slide is a portion of a recent map that combines data from a recent satellite called Planck and the ACT data. All right, so this is a commonly shown slide because it's just a lovely graphic to summarize the history of the universe. So time is increasing from left to right on this slide. And the thing about the cosmic microwave background is that it emerged from a much simpler time in the universe, when the universe was just full of plasma with only teeny tiny variations in the plasma density. And as the universe expands and cools, the plasma cools off enough to release the radiation that it had in it to travel virtually unimpeded for the next 14 billion years. And the reason that happens is when the plasma cools off enough, there's no longer sufficient energy in the radiation that it contained to be able to break apart hydrogen molecules when they form. And so the contents of the universe become neutral. You no longer have the distracting presence of electromagnetic ionized particles to interfere with the radiation as it tries to travel. So what happens is that patterns arise in the CMB, as we'll see in the next few slides, that are due to well understood physics. So gravity, electromagnetics, simple harmonic motion. And those patterns allow us to deduce fundamental properties of the early universe, including the relative proportions of its contents. All right, so how about what does the CMB look like if you try to visualize it? So here's a map of the CMB from the Planck satellite. And in this case, the color scale is about plus or minus 300 millionths of a degree. The overall average temperature of the CMB, cosmic microwave background, is about 3 Kelvin. So that color bar scale is about plus or minus 100 parts per billion. And so it's very smooth. So the thing that jumps out at you when you look at this map is that nothing jumps out at you. It's just kind of boring. It's got little bumps up and down. And so instead, we like to look at it in so-called harmonic space. So what's plotted on the left is the result of taking the data from the entire celestial sphere and expanding it in spherical harmonics, and then taking the coefficients of those expansions and averaging them over the multipole moment m, which has to do with whether or not there's any directional dependence to the CMB, and then looking at the square of that averaged coefficient. So that's what's plotted here. Roughly speaking, on the y-axis, we usually multiply by a few constants here and there. But the thing that jumps out here, as compared to the map of just the CMB, is that this is a rich and exciting structure when you plot things like this. By the way, I titled this slide Gaussian random fields because that's what we think that the fluctuations in the CMB temperature are, and also in its polarization, as it turns out. They're represented by a Gaussian random field, which means you can compress all the information to just a power spectrum like this. There's no preferred direction, and you don't lose anything by doing this compression. I should say both temperature and polarization are shown in this plot. The temperature is the curve on top, and the polarization is represented by these two things called E and B, which are below, which I'll say something about in a minute. Right, so the structure is rich, and so we model it. Okay, and we think we can model it because we think that we understand the physics, as I claimed before. So what we think is happening is that back in the early epoch, when the plasma existed, there was an underlying three-dimensional power spectrum field, and we don't have that much information about it, so we just model it simply as shown here, where K is a three-dimensional wave vector, and we just estimate that it looks, the power spectrum looks as shown. And what we find, even though I just said, oh, it's boring to look in real space, you should only look in harmonic space, we actually find that there's something somewhat interesting that you can do in real space. And this is a beautiful, to my mind, plot that came from the WMAP satellite. So there's the COBE satellite I mentioned recently, there's the Planck satellite, in between there's the WMAP satellite. And what the folks from WMAP did is the following. They took a map of the entire sky, and everywhere that there was a negative fluctuation, a cold spot, they stacked all of those cold spots on top of each other. And when they did that, they got something that looked like a well that was cold in the middle. It turns out that a cold spot like that is representative of overdensity of plasma in that region, for details having to do with the fact that there's a gravitational well in that location, and so the photons have to climb out of it, and that makes them look colder than if they hadn't had to lose energy by climbing out like that. Okay, so imagine being back in this epoch and being pretty far out, pretty far away from the center of this dip. And so, but you can't be not farther away than the information horizon, but inside that, which is about 1.2 degrees. And when you're that far out, then the only thing that matters to particles is gravity. So that means that the plasma, because of gravity, will be flowing inward into the center of this well. But as particles, or as the plasma gets closer to the well, like when it gets near the sound horizon, which is at about 0.6 degrees, then the inward flow of photons starts to be compressed, because you're trying to pile stuff into that potential well. And so eventually the plasma starts flowing back out again. And when that happens, you have plasma flowing in and plasma flowing out, and you see these interference rings. So that's what we're starting to see in this particular image. Okay, and so that process of plasma flowing in and out, it's a simple harmonic motion process, and so it results in the rich structure that you see with the peaks and wiggles in the power spectrum plot. Let me see. Oh, let me move to a new slide. Oh, good. Sorry. And so with that understanding, we can fit the power spectrum, and currently fitting the power spectrum, it only requires 6 parameters, and you can get a great fit to it. So the line that's shown in these plots here, the lines that are shown are due to fitting only 6 parameters, the 2 parameters that are in that 3D power spectrum on the top, and then 4 other parameters relating to the baryon density, the cold dark matter density, back at that epoch, the current dark energy density that we would need to have if we assume the universe is flat, and then the reionization optical depth. Because even though I said at the beginning that the radiation is released once the plasma cools down enough and travels unimpeded for the rest of the time, that's not quite true. It can actually scatter off some of the subsequent ionized particles in the universe. Okay, and then just a few more facts about the CMB. Like I said, the plot on the left, it includes not just the intensity fluctuations in the CMB, which we usually call temperature fluctuations, but also these polarization fluctuations. And in fact, on this slide, I've added this fact that there's actually a cross correlation between the temperature and the polarization, and here's why. So the acoustic oscillations, the process I was describing before is often called acoustic oscillations. So the acoustic oscillations themselves, they can create quadrupoles in the plasma. Sorry, let me just say, they create variations in the density of the plasma. And when you have densities in the plasma that look like quadrupoles with respect to a specific point. So in the diagram there, you're meant to imagine an electron sitting somewhere. And if the electron sees a quadrupole distribution of radiation around it, then when the electric fields from that radiation hit the electron, they'll cause it to radiate dipole radiation such that the outgoing radiation will be partially polarized. So that's what's indicated here. And the reason that you can, it's the reason that you actually can see quadrupoles locally. It's not, as I just falsely said, due to the fact that there's large density variations in the plasma, but instead because there's all that flowing going on, the flowing in and out. And so different parts of the plasma have different velocities, and so you get Doppler effects. And the Doppler effects are the ones that can lead to these sorts of quadrupolar patterns. And the cool thing about that is it means that the CMB polarization essentially traces the velocity of the primordial plasma. And so then you have the temperature, which is telling you about the intensity or number of photons in different places. So like the density of the radiation, and the CMB polarization is telling you about the velocity. So having the information from both the temperature and the polarization at once gives you extra information. And yet, as I said earlier, we can fit all of these power spectra with 6 parameters pretty well so far. And then there's a coda. So with respect to those other plots, the plot I showed previously of stacking on cold spots, what WMAP did when they published the temperature stack was they also published this polarization plot. And this polarization plot is so cool because it turns out that when you have plasma flowing in, if you picture when the plasma is flowing in and then getting faster and faster and faster as it flows in, then you'll naturally have a quadrupole. Each of the electrons that are in that flow will naturally have a quadrupole. around them, because the particles in front and behind them will appear to be receding, and then the neighbors appear to be coming closer. And so that gives you this tangential radiation pattern that you see over here. This tangential, ooh, I can't put my cursor in the right place anymore. Okay. Anyway, on the right, you get that tangential pattern. And then when the radiation starts, when the plasma starts flowing back out, you get the opposite effect. If you think about the signs of the relative velocities switch places. And so now instead of getting like a tangential polarization, you get this radial polarization. And that is interesting because radial and tangential polarization patterns, they have a specific symmetry. So they have the symmetry that if you look in a mirror, they look the same. So they're even parity, even spatial parity. And we call the reason that the power spectra on the left are called EE and BB is because we call the parts of the polarization that demonstrate this type of even parity, we call them EE. And then you could have patterns that do not demonstrate that and instead would have the opposite sign if you looked at them in the mirror. They'd look like they were flipped if you looked at them in the mirror. And those we call BB. And it turns out there's a huge story around EE and BB polarization, because the BB polarization is not naturally produced by these acoustic oscillations the way the EE is. And so there's another possible primordial source for it, which is gravitational waves left possibly from an early epoch of inflation in the universe. But I'm not going to talk about that story today. Instead, I'm going to start talking about the ACT instrument. And so in terms of the overall storyline, the predicting the universe today from looking at the past with a big dish in the desert, now I'm talking about the big dish in the desert. But to do that, I would first like to recognize the gigantic ACT collaboration, of whom several members are on this panel today. And I'm delighted they agreed to do that. So the ACT collaboration, it's large, it's really hardworking, and it includes a lot of what I would call science heroes. So I really want to thank the team for all their work on fronts, both experimental and analytical, and for them also specifically for the many materials they have made for talks like this one that I will be enjoying. So this year, the picture here is from 2019 because we didn't manage to have a face-to-face meeting this year. But if you look closely, you can see some of our Chilean colleagues, some who are on the panel, some who are not, including Rolando, Cristobal, and Pato Gallardo. I think those are the main ones who showed up in the photo. So I previously mentioned the Planck satellite. The Planck satellite has done remarkable work, made very beautiful maps of the entire sky, particularly nice maps in temperature. But because it was a satellite, it had the mirrors and it had limited physical size. And so its resolution is somewhat limited. And ACT was designed to be complementary to Planck. So it was designed to make really high resolution CMB maps. And those maps, it turns out, enable just a gigantic range of science, most of which I'm not going to get to today, but some of which might be important to some of our panelists. So, as y'all know, better than I do, the Atacama Desert is what I would call a bone dry desert, a really dry place. So ACT is sited at 5,200 meters in the high Atacama Desert in Region 2. As you can, well, y'all are probably used to looking at satellite pictures like this that make it kind of clear how dry the desert can be. And it's really great for us. Literally, the dryness is really great for us because water both absorbs and emits microwave radiation. And so for us to be in the driest possible place gives us the clearest possible view of the microwave sky. And another great thing about Chile and the location of ACT is that it's kind of close to the equator. So it's at 23 degrees south. And there are two main fabulous sites for looking at the CMB. Okay, three. Space is pretty good too, but one of them is this site, and then one of them is the South Pole. And the South Pole, the thing about the South Pole is because it's at the pole, it can only see a sort of like a cap, a small, not the full, not nearly as much sky as you can see if you're located near the equator as we are. So it means it provides this nice complementarity between instruments that are located in the Atacama Desert versus ones that are located at the South Pole. Okay. So ACT, it's a 6-meter off-axis telescope. Being that size for the frequencies we're operating at gives it arc-minute resolution. And I already said it's high and dry in the desert. So these are some early design pictures showing the fact that the 6-meter primary is made out of a number of panels, 72 separate panels. Each individual, oh, maybe I'm going to say this on a later slide. Each individual panel has a really nice machine shape that's good to around 2 or 3 microns compared to the figure it's supposed to be on. So this is the 6-meter part, and then there's a smaller 2-meter secondary reflector, and the entire instrument is inside a gigantic 11-meter ground screen, which protects it from the 300 Kelvin radiation from the ground. And then these images on the right are showing, they're showing the ray trace. So the light comes in, hits the large mirror on the right, and then hits the secondary mirror, and then goes into the receiver, which is in a little cabin that sits underneath the rest of the telescope. Okay, so here it is in real life. The telescope, it looks a lot like the other picture, I like to think. And you can also see where it's situated on the plateau in the Parque Astronómico Atacama. Is this large flat plateau. You can see we do have neighbors off to the left. It's becoming quite a great site for Chilean observations. Before we actually went to the field, we had prototypes to test the camera. There's one on the left that we put on the roof at Princeton. And then there's one that one of Rolando's colleagues back when he was a graduate student made out of gingerbread. So, and then also just a few fun photos, I think, to show, I don't know, grittiness. These are pictures of the telescope when it was first built in Vancouver and then shipped to Chile. And these are some pictures of it being loaded onto the boat. And then on the right is a picture of the 72 panels of the primary mirror as viewed from the top of the secondary once it got there. And what I wanted to say about the telescope is that the 72 panels, each panel only has 2 to 3 microns surface roughness, but then we have to put them all together and have the whole shape of the mirror be the shape that was designed. And that can be done because there are little actuators that you can move the panels from the back to put them in position. But you can only do this with a really careful set of measurements of where the panels actually are compared to where you want them to be. And our whole program of getting that to work out has been led by Rolando Dunner. And it is not false to say we couldn't have done anything without that work. So, okay, so I somehow have, sorry. I can't read my own title, but that's all right. One of the interesting things about the way we put together the camera was something that was novel in 2007 when we were doing it, was that we separated out. So it's kind of like 3 cameras stuck in one cryostat. And that was unconventional at the time because a more typical thing to do was let all the light come in and then break it up into its different frequency components after it had entered the cryostat. And we decided it'd be better to keep different frequency components in their own set of optics. It's modular. It means that many components can be smaller. It turns out it's easier to get good image quality because you can control, you're handling a smaller amount of the focal plane as you try to design the optics to get rid of imperfections. Another thing that we did was we used silicon to make the lenses. Silicon is a nice thing to use because it has a high dielectric constant. On the other hand, it's a terrible thing to use because it has a high dielectric constant. And so that means that there's huge reflections when you go from the vacuum of the cryostat or the index of air onto this n equals 3.4 lens. There would be a huge reflection. So you must make a good anti-reflection coating. The way we're doing that now is led by our colleague who used to be in Michigan and is now in Chicago, Jeff McMahon, is make these so-called metamaterial coatings where you literally just remove material in a smart way. So you adiabatically go from the index of air to the index of silicon. And one of the lenses made in such a way is shown in the bottom right corner. Nice. Okay. So another novel thing about ACT is that we operated at 100 millikelvin. And we do that using a dilution refrigerator. So it seemed kind of crazy in 2014 to take a dilution refrigerator up to 5,200 meters. Things like that were not common, but we really wanted to do it so that we could get down to these really low temperatures, which makes the detectors more sensitive. And we end up getting more cooling capacity, and you can run the instrument 24/7 without ever having to warm it up to recycle it to get it cold again. It turns out that this sort of gamble has paid off for us, and it's also a widely used way of operating these days. And I have to say that there, my colleague Mike Niemak, first Kent Irwin at NIST, and then Mike Niemak really pushed that we should operate these detectors at 100 millikelvin and that using a dilution refrigerator would be fine. And again, listening to them really paid off. So this is the same picture as shown before, showing what the cryostat actually looks like and its contents, but I rotated it so I could do a really fun effect where it turns into the real thing here with then graduate student Patty Ho in the actual high bay that we have at 5,200 meters near the telescope. Another thing that it's fun to talk about, to my mind, about ACT is the type of detectors that we use. So we use so-called transition edge sensor bolometers, and the transition edge sensor provides the thermometer that you need when you have a bolometer. So a bolometer is just an absorber that has a weak thermal link to some cold bath temperature, such that when radiation impinges on the absorber warms up. And then you measure how much it warmed up with a thermometer. So the TES is a superconductor that's held near its critical temperature, so it has a very steep change in resistance so that you can measure the temperature well. And a really fun thing about the TES is that if you put that resistor, if you put a voltage bias across it by putting a really small resistor here, and then you have a little parallel circuit, I think I showed that in the image. Then with a voltage bias, when the thermometer heats up, its resistance goes up, and that means that the electrical power that's being dissipated also on the absorber from the thermometer, that looks like V squared divided by R. So when R becomes large, the extra amount of heat being deposited on the bolometer goes down, and that's a negative feedback that allows you to keep the device at a constant temperature and operate it like this. And then we use some really cool tricks as well that were invented at the National Institute of Standards and Technology to multiplex the detectors so we can read out the thousands of detectors. Just partly to make Rolando smile, I'm going to show you this old school photograph of the first camera detector array that we used for ACT. It was this array of 32 by 32 1 mm square absorbers, and a few are missing. That's why you see those empty looking squares. And it was made in this crazy way that our colleagues at Goddard had invented, where you take a piece of silicon and then you make a little, a 1 mm square that's very, very thin. So only a couple microns thick, and the rest of the silicon is like 0.5 millimeter thick. And then you make these tiny little legs that you see in the right side photo, and then you can just fold the silicon, causing those legs to just bend as you do it. And then when you're done, you end up having just this array, this row of squares, like the top row of squares you see on the left. Now, what's more modern now is what we're doing, what we did for the second ACT camera, where we had these arrays of detectors that were two-dimensional. But for our second camera, we had to use 6 of these hexagonal arrays and fit them behind this set of feed horns. And then we had to have these 3 other funky shaped ones that we called semi-hexes and put them all together. But for the second array, aside from this two-dimensional change, we also started using detectors that were polarization sensitive, unlike the previous one. So we were able to measure these E and B modes. And then, and that's a picture of one of the arrays when it was completed. And then for our third ACT camera, I say that it's not just modern, but it's downright blissful. And the reason is that now we make the detectors the same size as the feed horns. So now they're 150 millimeters. It's all made on one detector array. And then we put supporting electronics around the outside. And another thing that's made our lives really, really great is we changed the material that we use for that superconductor in the transition ed sensor. And it just turns out that this material is very stable and reproducible and easy to use. So, and then one other thing I should say is this most recent ACT camera and the previous ACT camera, they're both polarization sensitive, and they both have some different frequency components that they're sensitive to. So the previous one, there was one camera that operated at 100 gigahertz and 150 gigahertz, and then 2 more that worked at 150 gigahertz. And now with the third ACT camera, we have one array that can operate as low as 30 and 40 gigahertz, and another that can operate at 150 and 220 gigahertz, and then 2 that operate simultaneously at 100 and 150 gigahertz. Here's more people in the lab after completing arrays. Okay, so I'm gonna switch gears to tell you the last thing about ACT and how all of that instrumentation is used to make a variety of measurements, but I'm only going to mention one. But before doing that, I just had to pause because, as you may know, my colleague Jim Peebles was awarded the Nobel Prize a little over a year ago. And when he was being interviewed on the phone, he made this comment about how at the time that he was starting to head into cosmology, he was uneasy because the experimental observations were so modest. And I think that he now feels otherwise. And I'm happy that ACT is part of the surfeit of data that we have for cosmology now. Okay, so a little bit, so I want to talk about ACT and the Hubble parameter. So the expansion of the universe is described by a scale factor, A, and that's like gives you a typical size in the universe, and the fact that the universe is expanding means that typical size is getting larger. The Hubble parameter is defined as shown here as the derivative of A divided by A itself. And there are a few more definitions that today, the value of the scale factor, we take it to be 1. Okay, so it used to be smaller in the past. And then we define the value of the Hubble parameter today as H0. Then for those of you who like to think about redshift instead of the scale factor, the relationship between A and redshift is this inverse one that's shown here, except you have to add 1 to Z before you Come on. Okay, and the idea that I want to get across in this discussion of ACT and H0 is that you can predict the universe today from having looked at the CMB, which was looking at the past. And of course, we did it. In our case, we did it with that big dish in the desert. So here's just a picture of the power spectra as measured by Planck, just because this is the slide I had in my slides set. But by the way, if they look slightly different than when I showed them to you before, I'll just give you a secret. That's because in this case, the y-axis is linear. And also when people show you this type of plot, often strange things are going on in the x-axis. Like if you look at the x-axis here, there's some interesting binning that's going on. So people do things just to make it easier to see interesting features in the spectrum. Okay, so then this is a figure from this marvelous online tutorial about the CMB from Wayne Hu at the University of Chicago. And the idea of this picture is just to remind us that co-moving distances are related to the diameters that they subtend according to the geometry of the universe, okay? But we are going to just posit that the geometry of the universe is flat. And so then the ordinary sort of triangle that you would draw, if you knew a distance in the past and you knew how far away it was, then you'd be able to say what the angle it subtended is. Oh, I have another picture here. Oh yes, flat. We're gonna posit that. And so what we can do next is say that there's an interesting length scale that I already indicated on those earlier plots of stacking on the cold spots. So there's this interesting length scale, which is the sound horizon. So how far sound could have traveled in the primordial universe. And the co-moving sound horizon is related to a particular angle theta s, which we can see in many places in the primordial power spectrum due to the way that the acoustic oscillations themselves show up in the power spectrum. And so it's quite straightforward to determine this theta s. Okay, and we think we know from straightforward physics what r sub s is, the physical length scale is. And so, well, okay. As I said in the corner of this plot, the physical length scale rs, the sound horizon, it does depend somewhat on the Hubble parameter, but I'm going to explain why we don't worry that much about that. But then this distance, this angular diameter distance between us and that surface of the surface of last scattering, which is the time that the CMB was released toward us, that parameter d sub a, it depends on the Hubble parameter, because the Hubble parameter is describing how the universe is expanding as time goes on. And so how the universe expands determines how far away that epoch is. And then there's another simplification, or there's another fact, which is that from Einstein's equations and then their repackaging by Friedman, we end up with this relationship between the Hubble parameter and the energy density of the universe. Okay, so rho is just the energy density of the universe, and it's simply related to the square of the Hubble parameter. And we know a lot about these energy densities because the energy density of matter, for example, it just gets smaller as the scale factor cubed, because it's just, you know, a number, it just goes like the volume. And then the radiation, it gets smaller like the scale factor to the 4th power, because there's the dilution due to volume, but there's also the fact that the temperature gets smaller. And then neutrinos, they're an in-between case because they're like radiation early on when they're super hot and zipping around a lot. But as the universe expands and they cool, they begin to act more like matter, but we can figure that out too. So that's a curve for what the energy density in neutrinos might look like. And then dark energy, it has this crazy feature that the idea, if it's lambda, would be that there's just a constant value of the dark energy density at all times. So that's what's indicated here. So just from those types of curves, you can draw this cyan curve of the trajectory of the Hubble parameter as a function, in this case, of redshift. I could have done it as the scale factor. And this particular value is normalized so that it hits 1 today. So you'd have to multiply it to give it units. What have I done? Okay, so then I said before that the sound horizon depends somewhat on the Hubble parameter, but the cool thing about that is the sound parameter, of course, only depends on the Hubble parameter from early on up until the epoch of the CMB, because it's a distance that existed back at that time. And this picture was meant to convince you that we know a lot about the universe. Practically all that matters about the universe before is that it was full of a lot of radiation and a certain amount of matter. We don't need to, the dark energy is so small compared to that we can ignore it. And then, but it does depend on the baryon density, which we attempt to measure from the shape of the CMB pattern. And the photon density is known very, very well because we measure the CMB temperature today. So that tells us the number of photons per cubic centimeter. And so we're left with the H of Z then depending on the matter density. Okay, but then, so in short, the sound horizon depends on the dynamics before dark energy began to matter, but that's not true for this co-moving angular diameter distance. It depends on the recent dynamics. And just to show you these plots, just so that you can, in your own mind, be integrating over Hubble's constant. This is a plot for lambda CDM, and this is a plot still for a flat universe. And so the matter had to get bigger when I said there was no lambda CDM. And you can see the trajectory of H of Z changes. Okay, so the idea of the hubris of the CMB argument is to say, well, we measure these parameters of the early universe. And so we can just take those initial conditions and some little other piece of information, such as the thought that the universe is flat, and some bit of information about the amount of dark energy that we have today. And then we can just guess. We can just make a plot like this cyan curve here that tells us what Hubble's constant should be today. Aggravatingly for this image, I normalized it so it was 1, but I didn't have to do that. We could have kept all the units on it. And so that's the idea, is we can take the CMB, and then we have to have one more recent tracer to break degeneracy. But we can basically take only information from that early universe epoch, and we can just predict what Hubble's constant should be today. Well, as has been pointed out multiple times by Adam Rees especially, that doesn't give the same result as if you just use supernovae and try to measure Hubble's constant today. And Adam Rees has moreover noted with his colleagues that in general, if you take early universe measures and try to do that propagating forward argument, you get different results than measurements that he's listed here, which are dominated by the supernova measurements of Hubble's constant. Okay, so right, just the plan would be that CMB defines the initial conditions of the universe. That determines how the universe expands, and that lets CMB predict the future, but it's not easy. The errors are small, and what's shown in the left plot is the status, the thing that's circled there is showing the measurement that was done, this way of estimating what Hubble's constant would be by Planck in 2018. Their errors were really small. But the effects of Hubble's constant on the CMB spectra are also really small. So my colleague Simona Iola made this lovely plot just demonstrating how similar the power spectra would look. So it's the difference between this kind of gray colored plot and this blue plot for the low and high H0 values. So it's hard. So, oh, and I should say, it makes you go, well, what if Planck, just the satellite, has an error, has some sort of systematic effect that makes it hard for them to make this measurement? And there was a paper in 2013 that tried to just estimate Hubble's constant without Planck, but it was not super constraining, as you can see here. And so then that's where we wanted to come in with the data from the Atacama Cosmology Telescope to try to make a measurement that would have comparable strength to Planck's, to see whether we could rule out the possibility that Planck just had some systematic effect. So I will go quickly through these last slides because I think we're starting to run out of time, but not without pausing to point you all to the young team members of ACT who really drove forward our two papers that describe our data release 4 that we call DR4. So led by Steve Choi and Simona Aiola, but with other strong contributions from the folks shown in the lower right. What's pictured here is the sky coverage that we have to examine the CMB. What's shown in the black, that snake-like thing, that's the image of our galaxy. So it's some strange coordinate system that has taken our galaxy that ordinarily would just look like a band at the equator and moved it to here. And the darkest colors on our plot, the dark red, that indicates where we have the most sensitivity, and the light blue and cyan colors are places where we have less. This is kind of a plot that tries to get across what ACT can bring to the picture when you have such an amazing instrument as Planck already in play. So Planck makes measurements of the entire sky, and that's what's shown on the top left, but ACT has measurements of almost half the sky. What's shown on the right are not the ACT data, it's the Planck data. It's just trying to show you the coverage that ACT has. But ACT has much more resolution. So on the left here, you see the Planck data, and then on the right, you see what happens if you combine the ACT and Planck data. And you can see that what looks fuzzy over here begins to look more defined over here. And in specific, you can see point sources, for example, in red pop out, and other small features pop out. Another thing that ACT brings is sensitivity to this polarized signal, the E modes. And that you can perhaps see on the bottom here. The Planck's data are mostly noise. So that's like, it's the same color stretch for the left and right figures, but the left, since it's noisy, it looks brighter with just random noise. And then when you combine ACT and Planck, you get the boring and yet features of the polarization that pull out. And then you may not be able to tell from this plot, but there's similar sensitivity to the temperature, except ACT is not sensitive at low multipoles. So it doesn't make good measurements of the largest features in the maps. And so what we do with the ACT data is we combine it with WMAP, that other satellite that made really great measurements of the largest angular scales. That's what we've done. I'm going to skip this. This is just describing where ACT is sensitive compared to other instruments, and just go to the end. So ACT weighs in, and it turns out that ACT and WMAP support the Planck result. Since ACT was really much more sensitive in polarization than Planck, this is saying that measurements that have a huge contributions from the polarization, which is tracing the velocity back in the early universe, gives the same result for H0 as the measurements that we had before that didn't have so much polarization or velocity information in them. And so there you go. We weighed in and we said that we didn't see anything wrong with Planck. And so it really looks like measurements from the CMB differ from measurements from the supernovae data. And just one last tiny slide. I'm also involved, I'm actually the spokesperson of this instrument called the Simons Observatory that aims to be sited up in the Atacama Desert near ACT. And it's a really gigantic collaboration, but that includes all of the ACT collaborators, plus many other collaborators, including those from the project called Polar Bear and others. And with the Simons Observatory, we'll be able to make even better measurements of H0 than we already have. So thanks again, and thanks to the ACT collaboration in particular.
Wonderful, thank you so much. This was a fantastic overview of the ACT measurements, and now I'm going to open this up to the discussion. So there are various questions in the Q&A. Let's start with a very simple question by Francisco Jara. How do you explain the difference in the values of the Hubble constant? Any theories? Any preferred theories? Let's put it that way.
Well, I think that there have been a number of papers that have pointed out that the simplest thing that jumps into your mind doesn't work. Like you might say, oh, let's just make the dark energy really big early on and then small later. And there are various reasons that simple solutions seem not to work, or maybe it's just that you would need the simple solution plus, plus another trick to get the simple seeming solution to work. I guess that, just because I work on CMB experiments, I wonder if there could be a problem with the supernova measurements.
Yeah, the supernova measurements have very independent, similar, let's say, orthogonal methods that underpin the supernova offsets. So
well,
I think
it's very interesting, the whole tip of the red giant branch measurements yeah.
There's also the masers, right? So there's a geometric measure as well that seems to coincide with the supernova.
True.
Yeah, so.
It's so bizarre. I actually had to describe to my graduate students recently because they didn't know that we used to fight over H0 like this in exactly the same way. It's just you're talking about 50 versus 100. So it's
a different fight though these days. Yes.
Yeah.
Interesting.
I'm wondering what the panel thinks. Does anyone on the panel have a guess? Or
I open it to the panel. Please go ahead.
Okay, regarding that issue, I would like to know exactly how you measure your errors in CMB-based Hubble constants, because I think somebody, I'm not going to try to guess who, because it could easily be the Galaxy people, and it could just as easily be the CMB people. It's most likely both, I'm guessing, are underestimating their error bars, not accounting for some kind of systematic that they don't think of. So how do you estimate the errors with Hubble constants?
I mean, the whole, I'm not sure if this is your question, but the whole program is done by, examining the full cosmological space and looking at the likelihood and then marginalizing over all the parameters, all the other parameters.
It's like a Bayesian kind of thing.
Yeah, and we do put in some nuisance parameters, for example, the fact that we see point sources in the data. I didn't talk about that, and the spectra I showed you didn't show them, but point sources in the data, they show up at large L. And so, but if they're literally just Poisson noise, then you really know their shape. You just don't know the shape that they will take in the power spectrum. You just don't know their amplitude. And so that's a simple example of one of the nuisance parameters that we marginalize over.
Okay, so it sounds reasonable, but as Bayesian statistics does try to take into account kind of realistic scenarios. read out the unrealistic ones, but also take into account all kinds of realistic scenarios together. So another question I have is more of a technical observing kind of thing, is at the edge of your ACT images, do you get any kind of distortions in the images like you tend to get with optical or near IR when you're looking at the edge of the sky or at the edge of your detector?
No and yes. So what we get is, in order to make our maps, we have to observe the same spot in the sky like zillions of times. So that we scan the telescope back and forth, but then we collect data for literally years. And so we have many different like data samples that we add together in order to estimate the value of the map. And what that means is at the edges of the map, we don't have nearly as many observations because we take the whole array that has thousands of detectors and we scan it back and forth like this. And then at the edges, you've only sort of visited it a small number of times. So we have effects at the edges that we really have to worry about that are due to that process, that like the noise is different as you move around on the map. And,
I see. So it's not so much distortions as it is larger error bars.
Right.
Okay, because in optical and near IR, you tend to get both, and more so in optical, of course.
Yeah, I think the thing is our resolution is really small compared to where the meat of the data are. So in that sense, we worry less about direct stuff that happens in the optics and messes up the beam. That's way too cavalier. Rolando's scowling at me. We of course do a really good job with measuring it, but it's not, I don't think it's as direct as the comparison to optical. Yeah.
Okay, so I'll let other people ask questions now. Thank you very much.
All right, should we go to Julio next?
Yes, thanks, Thomas, and thanks, Suzanne, for the talk. I mean, this actually wasn't my question, but I can't help myself but wade into the H0 question. I mean, H0 is, as you were pointed at the beginning, the ratio between a distance and a velocity. And that is directly measured locally. H0 from the CMB is a parameter on a model that has many other parameters as well. So I was just wondering, if you were to take at face value the value that is locally measured, what would change in the interpretation of the CMB? What would be the sacred cow they have to kill in all this analysis that you have of the CMB to say, oh, okay, H0 is not 66, it really is 73, whatever. So what would it be they have to give up that is so important?
Well, that's related to Thomas's question at the beginning, which is that I don't think anyone has, been able to describe a model of the universe that would take us there. I
was thinking about the models of the universe, I was thinking about the data. You imagine it is, you impose a prior, there is 73. You go to your data. What is it that changes that you have to give up? What is the main, is there like one single thing that is so clearly consistent with that assumption that you can single out?
No, it really is this inner web of things that get you to the actual value of H0. Like if I guess it's a game like with the Bayesian statistics. If you're allowed to hold a whole lot of goalposts fixed, then you could ask how much does the CMB change? So that's what that plot that Simone Iola did, was it held everything constant except H0. And you saw it just makes these small changes, and so it makes changes in, I only showed the temperature. I think I showed the TE power spectrum. It makes, changes in the different power spectra. So, you could just say you measured all of those wrong. And that was part of the reason why having ACT look at it instead of just Planck was a good idea, because it seems like it's something that's really in the microwave sky that has that shape in the power spectrum.
Yeah, that's what I thought, unfortunately. Actually, my question was more about something you mentioned at the beginning, and you kind of skipped a little bit, which is what people call the real measurement that will, bring the third Nobel Prize to CMB observations, which is, the measurement of a polarization and the V modes. So, and then its interpretation, with inflation and all. I mean, how far are we from that? I mean, I guess you purposely steered away from that issue, which of course, also brought a controversy a few years ago. So what is our status there, and what is our, what is your prospect from ACT and other experiments as well?
Well, so those primordial B modes, they have an impact at large angular scales. And so ACT is really tuned up to make measurements at small angular scale. So that's basically the reason that I skipped it for this talk, and also just because it's a huge and rich, it's its whole colloquium itself. But with the Simons Observatory, we are building a number of instruments to try to probe it. And meanwhile, the team that thought they'd found it before has continued to expand, and they're operating in the South Pole, the other really good site, and they continue. And so I would say that between that team, Simons Observatory, and then this proposed gigantic CMB experiment that's being referred to as CMB S4, that would be a ground-based, not a satellite-based instrument, and the satellite called Lightbird, there's a lot of different experiments that are aiming at the goal is always to set the limit on the primordial B modes at about the place where you're pretty sure you won't be able to do better because of the foregrounds in our own galaxy. So all of that, what I would say is, how close are we to finding it? I don't know. How big is it? If it's big, it may already be sitting on disk somewhere, but
Didn't you have this in one of your first plots? There was this little wiggle of the primordial.
Oh yeah, right.
And component, and the errors were. I mean, the data was really close, as far as I remember.
Yes, but that has to do with how big it is. I forget what was actually plotted on that slide, but the shape of the primordial B modes pretty well from some straightforward-ish physics. It's the amplitude that you don't know. And so that was probably, I think it was showing an amplitude of this special R parameter that was 0.1. And that's really big. The goal is to be able to rule out 0.001.
Yeah, that's been ruled out already, 0.1.
Yeah, 0.1 has been ruled. Well, I can't remember what the actual number is, but close, yeah.
Great. Okay, so let's, before we go, Manuel has a question. Manuel, go ahead.
Okay, can you hear me?
Yes, go ahead.
Okay. Thank you, Suzanne, for the talk, a really great talk. I have a question about how do you distinguish between polarization from the primordial plasma and polarization from say the galaxies in between, or the matter in between, by scattering the dust in between?
That's a great question. So there's the question of whether or not the CMB will scatter off of stuff and gain polarization. That problem is literally the primordial radiation scattering off things. That doesn't happen very much, because there's only a 1 or 2% of the CMB scatters at all anyway off of anything else. So although people do, I mean, it is an interesting thing to see if you could look for polarization in when the CMB scatters off the electrons that are in the deep potential wells of galaxy clusters. So that is an interesting idea, but it's a really small signal. But the thing that you said about emission from our own galaxy, that was what was measured by the team that thought they'd seen the primordial CMB, was that they were seeing the fact that when dust grains in our own galaxy emit radiation, it's somewhat polarized. And so the method people use to try to distinguish the dust polarization from possible primordial polarization is this twofold thing. One is you try to have measurements made at a huge range of frequencies, because dust emits it doesn't emit like a 3 Kelvin blackbody. It emits like a whatever temperature it is thing that's sort of like a blackbody, but not quite. So if you have different frequencies, you can try to separate out the things that look like a CMB blackbody from other things. And then you can also try to separate out things that track other things in our galaxy, you know, patterns that look like other things in our galaxies, for example. But it's tough, and it's very likely that I mean, it's true, that's what's going to limit our ability to constrain the primordial B modes unless they're big.
Thank you.
Let's go to Indika next.
Thanks. Yeah, so thank you very much for the wonderful talk. So I wanted to ask, so when you showed the CMB map at the beginning of the talk, so there was a huge cold spot that appeared to be much more prominent than the rest of them. So as far as I understand, some people have claimed in the past that it is a bit difficult to explain this spot with our current theories of cosmology. So I'm wondering if this is still the case. Could you comment a bit on this issue?
Well, I think it's a whole issue of statistics. You know, people talk about the look elsewhere effect. So it is statistically unlikely, but how many possible statistical tests could you have done on the data set, and how many of them would have been unlikely, is the thing that's hard to, you know, sort of wrap one's brain around. So I think that's the current status.
Thanks.
Okay, and then let's wrap up with Rolando's question.
Okay, so thanks a lot, Suzanne. This was a very clear, nice presentation about CMB and experiments. And I want to take you to that aspect, the more instrumental side of things, and comment about how much technology has developed due to these experiments. From the, I mean, as you mentioned, the first experiments were very, I don't know, like very undeveloped, and now they're so super sensitive, which has been the main milestones that have happened during these years. How much of that has happened in the context of universities, and how much of this has been contributions from students, especially graduate students, and in that context, how much can you say that the quest for understanding the beginning and the large scale and the big questions about the universe is producing an impact on other aspects of society driven by technology and knowledge?
Wasn't that 3 questions? Let's see. How much? So do you mean both in terms of sort of human capital development, meaning that so many graduate students have, you know, contributed and made these instruments possible and then gone on and done other things? Okay, so that's one thing that I think has been true, is that one great thing, in my opinion, about working on anything in astrophysics is that people like it and feel engaged and empowered and want to actually work on it. So I know in ACT we've had what feels like unbelievable success with people who come in as graduate students or postdocs sometimes, and immediately are able to make a gigantic impact on how we do things. And then we have all this competition from other people trying to do similar things. And I guess they have some success too with having graduate students. And so those 2 things, I think the CMB has it has this amazing track record of people working on the CMB and then ending up getting faculty jobs, for example. So I feel like this work has had an impact on society in that way, that it's drawn in people and then been able to move them along to academic careers where they can then reach more people and get more people excited in this kind of pure science. But maybe you meant technologically. Well, I mean, I'm really excited by the fact that we use that dilution refrigerator. And a thing that I think is interesting is that the world of quantum computing really likes to use dilution refrigerators too. So I don't know, maybe we've we've helped bring them along in their quest of using dilution fridges.
Right. And what about other aspects like you talked about metamaterials for the lenses. If we compare the first detectors with the new detectors, all the work done with the people developing these TESs everywhere, there has been, I think, in my opinion, there's a huge development of new techniques, and who wonders what they will be useful for sometime in the future.
I think the thing is that it's like, I think things are mostly cumulative. I don't think somebody's going to take exactly the ACT array and then use it someplace else like that. But instead, they're going to take, the aspect of the ACT array that it proves that you could do this, that, and the other thing, and then that then puts it into the design for the next instrument, including those sub-millimeter instruments and instruments that go on satellites like Lightbird and so forth. And yeah, so I don't think there's anything that you'll take directly out of ACT and put into another project, but you'll feed the other projects.
Mm-hmm.
Okay, so we understand that you need to run to another appointment, but I have one last question, maybe a quick answer to this that surfaced here in the Q&A by Thomas Rojas. Is the Starlink project a real problem for the observations in this bandwidth?
We're pretty worried about it, yep, because of the radio frequency interference. Yeah, we are worried about it. I mean, I mean, there's been some work, some sign that the Starlink, the companies involved are somewhat sensitive and willing to try not to spill their radiation into every single bandwidth that we use in the Atacama, but it's definitely a concern. And if any of you who have any weight to protest or try to drive people to do a better job limiting the amount that these radio quiet zones get bashed by Starlink, please do it.
All right. Great. Okay, so thank you very much. Let's wrap this up here. All for joining us for Suzanne's talk today. And thank you, Suzanne, for taking the time to tell us about your exciting project and the future, potentially, right?
Yeah.
Please be so kind again, fill out the survey after we finish. Our next scheduled talk will be on October 30th, which will be given by Paul Heunigen-Hühner, who is a philosophy professor who specializes on general philosophy of science and research ethics. And the title of his golden webinar will be "What Makes Science Special? Why is Science So Reliable?" So that's a very actual topic. So please join us for that one again. And so stay everyone safe, stay healthy, and until the next golden webinar in astrophysics. Bye, everyone.